Good morning. How are you doing today? Hope it is going well. Today, we're going to talk about divergence tests. So, you might have come across this already a little bit, but if not, the idea is if you have some sort of improper integral, saying something going from like 1 to infinity of f of x dx, does that equal a number? Or does it just equal infinity? Or does it alternate between a bunch of other things? Well, that's actually a fairly big question. I kind of threw it out there as something that you just kind of answer on the fly, but really it's kind of a whole field of study, and that is divergence test. So if something goes to infinity, then it diverges. Also, if something alternates between one or two or many numbers, it also diverges. So something will converge if it converges on a single number. To make this simpler, remember kind of the basis for integrals was Riemann sums. So if we have a purple graph like so, this will be the y-axis, this will be the x-axis, and let's say we have, in this case, y equals 2 for all of x. And we want to do a convergence divergence test on this. Then what we're really going to be doing is looking for the area under the curve. And we can do that with Riemann sums. So we'd say that this is delta x, like so, and we'd add up all these boxes. Let's say each delta x is 1. So we'd have 1 and 2, so we'd have an area of 2. And we'd do 2 times the number of delta x's, and if it goes to infinity, then it'd be infinity. So in effect, we'd have one giant square here, which would be, this goes off to infinity, 2 times infinity. And this is probably a good time to mention that I completely abuse notation. I do not mean for this to be a formal analysis of divergence tests. This is just generally to get the right idea and just the information that you need to know for the AP exam. So if you're looking at this like, wow, can he write infinity? Shouldn't he write limit as a approaches infinity and then just write a? True. Yes, probably. I don't care. Doesn't matter to me. I abuse notation, and especially for this, since we're just trying to get the right idea. There are millions, probably not actually millions, but many, a plethora, if you will, of a cornucopia of divergence tests, and I'm only going to go over some of the bigger, more useful ones for these low-level, introductory, fundamental, we'll go with introductory. This introduction to divergence tests. So if you start getting, cold sweats due to my abuse of notation, just take a breather, and if you're getting cold sweats from my notation, you might need a little bit more formality than I have, because it's not going to get any better. Okay, so we're looking at series and sequences. So I just talked about a Riemann sum going to infinity of little boxes for y equals 2. And I kind of talked about it in such a way that that implied we went from, let's say 1 to infinity of 2 dx. And we took the Riemann sum of such. And our Riemann sum came out to 2 times infinity, which is even bigger than infinity, and yet exactly the same. We get 2x, infinity, 1. So it'd actually be 2 times infinity minus 1, which, as you know, playing that game with when you were a kid, you're funny looking. No, you're funny looking times 2. You're funny looking times infinity. And the other guy's like, well, you're funny looking times infinity plus 1. And eventually the smarter, more mathematical juveniles realize that funny looking times infinity is the same as funny looking times infinity plus 1. So this is basically infinity. So this would be this equation, y equals 2, would diverge. And so if this is an example of something that diverges, you'd think, wow, what could converge? So a quick, definitions. We're going to deal with something called series. You'll be introduced to sequences and series. So a sequence is just a set of numbers that are ordered, where the idea is that is your first number, and that is 1, 2, 3, 4, your fourth number. See how I counted there all slightly? Yeah, not too subtle. So that's what a sequence would be. A series would be adding of a whole bunch of numbers. So this would be a ... series. It'd be a series of numbers since you add them together. The concepts aren't too difficult, but sometimes when you're reading like a problem or they're trying to explain to you what to do, it gets confusing because it's good to know what they mean. If they say, what's the value of the last digit term for a sequence? Well, this one they're talking about 9. But if they say, what's the last term for a series, they might be asking you, what's the sum of all these numbers ending with 9? So that's the concept that they're going for here. And so what we're going to be dealing with are summations, which would be series. And these tie in well into Riemann sums, because the way we did Riemann sums is we would draw a whole bunch of boxes and then add up the areas of each box. And that's pretty much what we're doing here. So the Riemann sum with y equals 2 could be represented with the summation. This is a summation symbol. It means add up for every value n to infinity. And your first thought is, well, there's no n in there, so what this effectively does is 2 plus 2 plus 2 all the way up to your infinite term. So this will be the first term, second term, third term, etc. And as we saw with the Riemann sum, this would be infinity, or 2 times infinity minus 1, but let's not muddy the waters. It's just infinity. And so then another summation, sum that would seem more reasonable to you, or a normal person, would be n. So this would be 1 plus 2 plus 3 plus 4, and then it keep going all the way up. And this would be viewed as y equals x. And again, you could find out if it converges or diverges by taking the area under the curve. We'll get to this in a little bit. This is actually called the integral test. And the idea with this then is it's obviously not going to converge to a value, because the further off you get, the more you keep adding to it. So we actually want something that goes the opposite direction. All right, I'm going to clean the board up just a little bit. Get rid of some of this ink pollution. Ooh, cyan. I think that's cyan. So the first two, they kind of made sense that they're not going to diverge to a value, because the 2, it just stayed the same. It kept adding 2 every time. And the y equals x, or n, kept getting bigger over time, which is the exact opposite of what we're going for. Not that converging is bad and diverging is bad and converging is good. I don't know. It's not one or the other. Don't mean to be convergist. All right. So if we have a graph kind of like so, and we have, let's say, get rid of the numbers, the graph is going to look like this. Where when this will be y equals 1 over x. So this graph of 1 over x, and then this, if we actually drew this out, let's say this is, I know, terribly not to scale. The axes are totally, that's okay. So at 1, we're going to have a box of 1. So Riemann sum will look like this. And when we get to 2, it'll be 1/2. And then when we get to 3, it'll be 1/3. Then it'll be 1/4. So it'll be 1, 1/2, 1/3, 1/4. And so the idea here is if we took all of these numbers, this is actually called the harmonic series, if you're curious, related to music. I am not musically talented, so I will leave it at that. But this is the harmonic series. So the idea is you have 1 plus 1/2 plus 1/3 plus 1/4, and going on until you get plus infinity. I'll just leave it as 1 over n. It's like, well, does this converge to a number? If you add up all of those, do you get something that's finite, or is it, an infinite? And there's multiple ways to prove this. And the way I like to view this is the integral test. So the integral test is basically something along the lines of, and I'm being fairly informal here. If you rewrite it as an integral from 1 to infinity, this is called an improper integral because you have infinity at the top, 1 over x dx, what would this, if this converges, then the summation, the series will converge. The infinite series will converge. And if this diverges, then the infinite series will diverge. Well, as you should know, the integral of 1 over x will be a natural log of x. I know it's absolute value signs, but I have all positive limits of integration, so it doesn't matter. I know, I just don't like writing absolute value. It's a personal prejudice I have. So we'd get natural log of x of infinity minus, natural log of 1, which equals, this is 0, which equals infinity. This, because the natural log of infinity, though really, it gets big very slowly, but it still goes to infinity. And that's kind of hard to get the feeling for, because if you take your calculator, put in the biggest number you can think of, and then take the natural log of it, you're still going to get a reasonably small number. So the number of the infinity you need to plug in to natural log to get infinity out is really big. With that being said, it's still possible, mathematically possible. So the harmonic series, 1 over n, would diverge, because when you add up all of these 1 over n's, though it will happen very slowly, it will actually give you infinity. So if you're asked, hey, does 1 over n or the harmonic series converge or diverge? It diverges. And this turns out to be kind of a sort of a break point, where anything smaller than 1 over n will converge, while 1 over n itself diverges. Now I know that is said terribly informally, but you'll kind of get a feeling for what I mean in a sec. So if we take another example, 1 over n squared, and are like, well, does 1 over n squared converge or diverge? Then we can do some calculations. So I'm going to do this a couple ways. So first way we're going to do is we're going to do it through the integral test. So I'll take the integral of 1 over n squared. So we have integral 1 over n squared, and I'll do dx squared. I feel more comfortable with x's. It doesn't matter. That's probably a terrible thing to say. Boom, boom, boom. All right. X squared is equals 1 over infinity x to the negative 2 dx, which equals x to the negative 1, then divide by negative 1 from infinity to 1, which equals 1 over x 1 over infinity. It took out the negative and switched the limits of integration, which is 1 over 1 minus 1 over infinity. The 1 over infinity goes to 0. We're left with 1. 1 is a number, specifically not infinity, and therefore 1 over x squared converges, not as opposed to diverges. So then you could do the same thing with where you're like, well, what if there's something between 1 over x, 1 over x, 1 over x squared, and you have like 1 over, I don't know, n to the 1.1. You'd find out that converges as well. Anything with a power greater than 1 will converge. I said I was going to do it another way. I'm not going to. I'm just going to let the integral test stand for that one. So, moving on to another example, we have another fairly common series here. So what this is saying is we have 1/2, and then we add to that a 1/2 squared, which is 1/4. And then 1/2 of that will be 1/8. Actually, I'm going to change this one a little bit. Instead of starting at 1, I'm going to start this one at 0. We really couldn't start the other ones at 0 because then you'd be dividing by 0, and that's end of the world type scenario. But for a geometric series, 1/2 to the 0 actually works. And then this goes on for forever and ever and ever. A quick, I guess, nomenclature. So this is a geometric series. Geometric. And the defining factor of a geometric series is you have some sort of ratio. Oh, back to the eraser. Oh, ooh, blue. You have some sort of ratio, commonly denoted R, and that's raised to a power. Sometimes you'll see A times R to the N, and that's considered a geometric series as well. But I don't even bother really talking about this A because you can just pull it out the summation. If you think about it, 3 times 2 plus 3 times 3 plus 3 times 4, etc., 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 you can intuitively look at it and be like, okay, we'll just pull the 3's out and then multiply that to like 2 plus 3 plus 4, etc., 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 down the line. So I don't even really worry about that extra A that a lot of other people put in there. This is also, though, not just a geometric series, but it is also considered a power series. And a power series has to do with there being an exponent right there. Now, it's kind of like a square rectangle thing. All squares are rectangles, but not all rectangles are squares. So every geometric series will be a power series because it'll have that little exponent power in there. But not every power series will then be a geometric series. So a geometric series specifically has to have this. It's of the form of a ratio R right here with a power. Okay. One of the cool things about a geometric series is there's a formula, which you may or may not know, to solve for a geometric series. Specifically, we can know that the summation, this right here, equals 1 minus r to the n plus 1, where I'm going to say that this is n up here. I'm going to say n final, over 1 minus r, where r is then the ratio 1/2 right there. So we know, and this assumes that n initial is 0, but it doesn't assume that n final equals infinity. Does not assume. So if you have up here like 4, then this number here, n would be 4, which would give you 1 minus r to the 5th. Okay, so plugging our numbers in here, we would then have 1 minus 1/2 to the n final, which is infinity, plus 1, which is still just infinity, over 1 minus 1/2. And doing some simplifications. Oh, I just used orange. Just used gray. This goes to 0, and we're left with 1 minus 1/2, which equals 2. So if you add up all these numbers, 1 plus 1/2 plus 1/16 plus ... plus 1 over infinity. I know, abusive notation. I don't care. You would get 2. There's a really terrible mathematician joke, but you can go around your mathematicians people and they'll think you're clever. And the joke goes something along the lines of you have an infinite number of mathematicians walk into a bar. The first mathematician orders a beer or a drink or whatever. And the second mathematician's like, that looks pretty good. I'll have half of what he just had. And then the third mathematician's like, yes, I'll have half of the guy that just had half. And etc. Falling on towards infinity. And the bartender's like, I don't have time for this. Here's 2 beers. And the idea here is when you take half of a half of a half and you add them all together, this infinite sum, that series, will equal 2. And the idea is that the bartender, the man watching the bar, is clever enough to realize that. Yeah, it's not a... Is it a funny joke? I don't know. Are jokes even really meant to be funny? Can jokes be enjoyable, though not funny? I guess that's the whole point of dark humor. Is it? I don't know. Gallows humor? I would consider that joke gallows humor, though it is kind of a buzzkill. Okay, moving on. So, you're like, wow, so I have to know that special geometric thing, equation, 1 minus r to the n plus 1 over 1 minus r to solve this? No, you don't. We can do this using math. I guess that's math too, but using the integral test. So we will take the integral of 1. Can we do 1? Can we do 0? Let's do 0. What will happen if we do 0? Can we do 0? Maybe we can do 0. Let's try 0. 0 to infinity. And if for some reason we can't do 0, we can always add in the number or take it out. Because we know the first term is 1. So if I wanted to start from 1 to infinity, I just do 1 plus 1 to infinity. And that kind of flaky, yeah. I'm treading on thin ice, but I'm going to say 0 to infinity of 1/2 to the x dx. And your question is, wow, how do I solve this? Well, it's a little bit more involved than I like to enjoy. But if you don't remember, there's kind of a integral table for this, which I didn't tell you, but you may have learned somewhere in life. I never memorized it. My memory is the same as that of a goldfish. So the way this is done, I'm going to draw an arrow. That way I don't have to, I'll maintain, just to show that I'm going to maintain less formality with this section. So you have your x up here, e to the natural log of 1/2 of x. Move over the 1/2. which gives us e to the x natural log of 1/2 dx integral, and then we're going to do u substitution. So we'll say u equals x natural log of 1/2. Natural log of 1/2 is just a number, so we're going to have natural log of 1/2 dx. And then solving for dx, we have du over natural log of 1/2, which we could simplify a little bit, but I'm not going to bother. This brings us over to integral e to the u du times 1 over natural log of 1/2. Solving this a little bit further, e gives us e to the u over natural log of 1/2 to some limits of integration. But since I don't want to solve for my limits of integration, I'm going to convert this back into e to the x natural log of 1/2 over natural log of 1/2. Come over here, get myself a little more real estate, bring it home color. So then we have x natural log of 1/2 to the x, just undoing what we did earlier. I have a friend who calls that log rolling, so we'd be rolling the log uphill. Rolling the exponent up the log? I'm not sure. It's just a mnemonic. So then we have 1/2 to the x over natural log. Darn you, eraser. 1/2 natural log of 1/2 evaluated from 0 to infinity. So I'm going to rewrite this as negative natural log of 2. 1/2 equals 2 to the negative 1, and then you can take that with the log and move it over. So then this would give us 1/2 x over natural log of 2 from 0 to infinity, which gives us 1/2 to the 0 minus 1/2 to the infinity over natural log of 2. Whoop. Whoop. So we have 1 over natural log of 2. And I wonder what 1 over natural log of 2 is. This goes to 0. One over natural log of 2. 1 divided by natural log of 2. 1.5? 1.4? 1.44. So this gives us 1.44? Right. Because 2 is less than e. Okay. So the first thought is, wait a sec, we got 1.4 when we did the integral test, but when we actually solved it using the formula, we got 2. How is this? This is crazy. Well, the integral test doesn't give you the area under the curve for the summation. It's if anything, the summation, which is what we're actually looking for, is kind of like a Riemann sum, which is an approximation for the integral. And therefore, what you're really seeing is our approximation, which in this case is what we're actually looking for, our approximation is not exactly equal to the integral we just did, which makes sense. It would be as expected. So the boxes are not equivalent to the smooth curve that we just found the area under, which, yes, true. Okay, so don't panic that the 2 does not equal 1.44. 2 does not equal 1.44. 2 was never meant to equal 1.44, and I doubt 2 will ever equal 1.44. Though, when I am the ruler of a dystopian society, and I am some sort of terrible chieftain, that will be my first rule, q equals 1.44. And it will cause great animosity and strife and gnashing of teeth. Okay, so I'll leave this geometric series summation answer up here, just because it's so useful in life. But I am going to grab another, let's clean up these, unlock, delete, delete, unlock, delete. Let's grab our next example. Our next example is the comparison test. So you may have noticed so far that there really is no, divergence tests really aren't a machine where you plug in a formula, turn it around, and it spits out an answer. It's kind of like solving an integral. There's no set way of doing it. There's various techniques which tend to work, but there's no one solution solves everything. When you come across derivatives, you have a very set way of, hey, here's how you start, you have this situation, and you follow through. That's not the case for divergence tests, just like it's not the case for integrals. This is, some things just can't be solved, but we have a lot of techniques that work pretty well. And if you look up like divergence tests on the internet, you'll find lots of them. That's just the way it works. So when I'm here throwing just random, it feels like I'm throwing random tests at you, and that's kind of sort of true. You don't need to have a very in-depth knowledge of divergence tests for the AP exam, but it's good to have an idea of some of them, and most of them are fairly intuitive, because you're like, oh, the integral test is basically the same as making Riemann sums. Okay. And most of these tests are fairly intuitive. So I want to create kind of a spider senses, if you will. So you can look at a equation and be like, okay, that probably diverges, or that doesn't diverge. So we're going to talk about the comparison test. Oh, actually, one quick thing I wanted to say about the geometric series test. Should have remembered. So you probably figured it out, but if you have a geometric series, let's say you have R from n equals 0 to n equals infinity to infinity, R must be less than 1 for it to converge. If R is greater than 1, then you're going to get something that, so if R equals 1, then you're just going to get 1 the whole way through. And you'll get a graph that looks like this, with all these boxes that are 1 in height. If R is greater than 1, then it's going to get bigger over time. And it's only when R, this ratio right here, is less than 1, that you're going to get something that gets smaller over time. That's supposed to continue getting smaller. And so this R in the middle, this ratio that you're going to use for the geometric series or power series, has to be less than 1 for it to converge. Okay, back to comparison test. So comparison test is you take something that you know and you compare it to something that you don't know and see if there's anything useful that can be said about it. So for this example here, we have 1 over n plus 1. So you look at that and you're like, okay, that looks kind of like 1 over n, the harmonic series that we talked about earlier, which diverges. So if this is 1 over n, then we know that 1 over n plus 1 will look something kind of like maybe this. And the reason I drew it below is because we know 1 over n plus 1. We know that 1 over n plus 1 is less than 1 over n, because when we add a number to the denominator, the bottom, the whole thing will get smaller. And so it's safe to say that 1 over n plus 1 would be less than I'm going to change this real quick to start with 2. And the only reason here is that way when I do minus 1, it doesn't divide by 0 and end the world. Okay, so now if we have 1 over n minus 1, we can draw that up here on top, not drawn to scale, 1 over n minus 1. So now we're dividing by a smaller number. N minus 1 is smaller than n. Therefore, 1 over n minus 1 will be bigger than will be bigger than 1 over n. So we have 1 over n minus 1, 1 over n, and 1 over n plus 1. And so this is useful because we know that 1 over n diverges. Another way of saying that the area under the curve 1 over n down here is infinite. So we can use the comparison test with 1 over n minus 1 to say that, all right, if everything included in 1 over n is also included in the graph 1 over n minus 1, then 1 over n minus 1 has to also diverge. So if you think of it in terms of a bag, here's a bag, maybe a jar or a pot, and this is 1 over n, this is 1 over n minus 1, 1 over n plus 1, and we know this contains infinite number of marbles, and we also know that we can fit this jar into that one, and this must also contain an infinite number of marbles. Now, the reason I included 1 over n plus 1 is there's not really anything we can say with the comparison test with this, because we know that 1 over n plus 1 can fit into 1 over n, but that doesn't tell us how 1 over n relates to 1 over n plus 1. So what the comparison test says is if you can compare something that you know, in this case 1 over n, to what you're trying to find, then that could tell you some information about that. So the 1 over n plus 1 is put up there as a warning of you can't use the comparison test on that to show that it's infinite or it diverges or converges. It does diverge, but we can show that using a different test, probably the ratio test. But the comparison test will be used for 1 over n minus 1 to show that 1 over n minus 1, though, does diverge. And that covers the comparison test. So comparing a known graph to an unknown that you're trying to find. All right, so the next two tests that we're going to cover, I'm going to cover them next time. They will be the ratio test and the alternating series test. So far we've used all positive values, so everything involved in these numbers are positive. But sometimes if you have positives and negatives, you can get those to cancel out in such a way that it will help you out. Before we go, let's look at maybe one more example of how you can actually use the comparison test. So if we have, looking at an example, we could also do something along the lines of, let's say n equals 1 to infinity, n squared minus 2n minus 3. Let's see, plug in 0 there. We'll just make this like 5. There we go. And the whole purpose of that is just to make sure we don't get any negative values. N to the 4th. And we compare this to, if we break it up, we have n squared over n to the 4th minus 2 over n cubed minus 3 over n to the 4th. So looking at this, our biggest part we're going to have to be concerned with is the n squared. So this will be less than n equals 5 to infinity of 1 over n squared. You could also look at it as by factoring out the n squared. Because we have the negatives right here, we know that the numerator is actually going to be less than n squared. And so this is going to be less than n squared over n to the fourth, which is going to be less than 1 over n squared. And using the integral test, we'll make that semi-normal. Using the integral test, we know that this converges. And if this converges, and we know that this here is less than something that converges, then this will also converge. You'll also kind of hear this referred to as the squeeze theorem. And the idea here is that we have 1 over n squared here. We'll have n squared minus 2n minus 3 over n to the fourth, less than it everywhere. And it kind of has the idea of 1 over n squared squeezes the lower function against the axis. And that's another example of the comparison test. Okay, we will cover the ratio and alternating series next time, and I'll kind of round out what you'll need to know for the AP exam with regards to divergence tests. Thanks, I appreciate it.